Welcome to Group 2's DDMDA video. In this video, we're going to talk about Diclofenac. Diclofenac is a non-selective, non-steroidal anti-inflammatory drug, also known as an NSAID, which is used to treat pain, inflammation, and gout. As you can see, Diclofenac consists of a carboxylic acid attached to a benzene ring, which is known as a phenylacetic acid, a secondary amine, and a dichlorobenzene. Two orthochloro groups help with the twisting of the whole structure, which aid to the binding of diclofenac into the active site. For the pharmaceutical products, diclofenac is made under salt form using sodium or potassium. Diclofenac was discovered in the 1960s by Ciba-Geigy Company, now known as Novartis. They had the aim of developing an NSAID with higher activity and tolerability than the current drugs on the market. To do this, they assessed the physiochemical properties that were present on NSAIDs, and found that they shared a common partition coefficient at physiological pH of approximately 10, that they were weak acids with a pKa of approximately 4 to 5, and they had two aromatic rings twisted in relation to each other. Mefenamic acid and indomethacin were used as proposed models for a hypothetical compound. Since both of them act as inhibitors of the target enzymes, in this case COX-1 and 2, the two compounds needed to mimic the shape and structure of common substrates for those enzymes in order to bind effectively to the active site. In this case, the target substrate is arachidonic acid. By comparing the structure of all three compounds here, it can be seen that the carboxylic acid group is important, as it is present in all three groups, as shown. Hence, diclofenac was produced with the same characteristic carboxylic acid group. In order to make sure the new molecule was weakly acidic, like the other NSAIDs, phenylacetic acid was introduced. The other important characteristics found in arachidonic acid is the twisted chain on carbon 10, which rotate this part of the molecule upwards, as well as the conjugated system to restrict the rotation in the rest of the molecule. Therefore, based on the structure of indomethacin and mefenamic acid, two aromatic rings were introduced to diclofenac's structure to further restrict the rotation, which will lock the molecule inside of the COX active site. In arachidonic acid, the compound has a twisted position, so indomethacin and mefenamic acid also had two rings twisted together to mimic the shape, and therefore so too does diclofenac. The two chlorine atoms were added to diclofenac to maximize the twisting of the phenyl ring. By 1973, diclofenac was synthesized by Alfred Salmon and Rudolf Pfizer and introduced as Voltaren by the company Ciba-Geigy after they tested more than 200 analogues. The drug was launched in the UK 6 years later in 1979. Moving to the mid-1980s, diclofenac was confirmed to be as effective as other NSAIDs in the treatment of rheumatoid and osteoarthritis, with safety comparable to that of ibuprofen and naproxen, as well as fewer adverse reactions than the other NSAIDs on the market. The synthesis starts with 2-chlorobenzoic acid and 2,6-dichloroaniline as starting materials. They undergo a reaction to make this benzoic acid compound, which we will call compound A. From compound A, there are two available reaction routes. Firstly, the carboxylic group is reduced by lithium alanate to produce the alkyl group. The alkyl group is then substituted by chlorine. The molecule then reacts with sodium cyanide in the presence of dimethyl sulfoxide to substitute a chlorine for a nitrile group. And finally, in the presence of NaOH, the nitrile group is substituted by a carboxylic acid group to give diclofenac. Alternatively, the compound A can be heated to 280 degrees centigrade to form the following compound. It then reacts with oxalyl chloride to give the following molecule, which then reacts with aluminium chloride, and finally it follows the Wolff-Kishner reduction from a ketone to an alkyl group to produce diclofenac. As previously mentioned, diclofenac is a non-selective NSAID, which means it binds to both the COX-1 and COX-2 enzyme in order to treat inflammatory conditions and reduce pain. However, how does diclofenac bind to the COX enzyme to treat this inflammation? Let's first look at what happens in our body without using the drug. Imagine that there is damage to an area of skin tissue. Immune cells such as neutrophils and macrophages will be activated and together with the damaged skin cells will generate an inflammatory response by releasing inflammatory mediators. Some of the most important mediators are prostaglandins, the prostaglandins will bind to the receptor on a neuron, leading to depolarization and will further promote and amplify the inflammatory response. At the same time, they will send a signal to the brain to generate the pain response. To find the role that the COX enzyme plays, we need to look deeper into this part of the process. During skin injury, the phospholipids in the skin cell membrane will be metabolized to arachidonic acid by the enzyme phospholipase A2. This then goes through a cyclooxygenase reaction and peroxidase reaction carried out by the COX enzyme to give prostaglandins. This is the COX-1 enzyme and this is the COX-2 enzyme. Both of them are the enzyme target of diclofenac. In a normal environment, arachidonic acid will go into the COX active site and will be metabolized to prostaglandins. The double bond of the fatty acid will bind to the hydrophobic surface of the enzyme. However, in the presence of diclofenac, the drug will act as a competitive inhibitor, competing with the arachidonic acid for binding in the active site. The carboxylic functional group of diclofenac at physiological pH will be a carboxylate group, and will form an ionic bond to the cation site of the COX active site. The aromatic rings then bind to the hydrophobic region and block the entry of the arachidonic acid. COX-1 has a function in decreasing acid production in the stomach and maintaining renal blood flow in the kidney. Hence, inhibiting COX-1 can increase acid production, leading to stomach ulceration and bleeding. It can also cause kidney injury, which may lead to renal impairment. Because of its serious side effect on the kidney, diclofenac is listed as one of the triple whammy drugs, meaning that it cannot be used with ACE inhibitors or angiotensin receptor blocker drugs. The combination of these three drugs together lead to acute kidney injury, a sudden damage to the kidneys, causing them to lose their function, or in even more severe cases, kidney failure. COX-2 plays a role in the cardiovascular system, which if inhibited will contribute to negative effects on vascular homeostasis and integrity, which can cause an increased risk of heart attacks and can lead to a stroke. All the side effects previously mentioned are serious. However, as a result, they are very uncommon. The common side effects, which happen to roughly 1 in 10 people, include stomach pain, heartburn, diarrhea, and in the topical or patch forms of diclofenac, local skin rashes can also occur as a common side effect. This is the end of the video about diclofenac. I hope you can take away some of the key information regarding the drug, such as diclofenac is a non-selective NSAID used for anti-inflammatory and pain reduction treatments. It was first discovered in the 1960s and was synthesized in 1973 based on indomethacin and mefenamic acid. It has higher activity and tolerability. Diclofenac acts as a competitive inhibitor, inhibiting the active site of both the COX-1 and COX-2 enzyme. It does this through sterically blocking arachidonic acid from being metabolized to prostaglandins, thus reducing the inflammatory response. The drug has serious side effects on the stomach, kidney and cardiovascular system, and is one of the triple whammy drugs. Its common side effects include stomach pain, heartburn, diarrhea, and skin rash. For a more detailed view of diclofenac, please click on the link in the description box below to see our research summary and our list of references used for this video. Thank you for watching.